Hello. This video shows the solutions to all three problems from the 14th International Physics Olympiad, which took place in Romania in 1983. Here I used artificial intelligence for the first time to read text in Russian and English. 14th International Physics Olympiad 1982 year IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. Email fred1996@hotmail.com. Skype name Eduard F. 1996. Problem 1. Jumping particle. 8 points. Jumping particle A moves along the positive axis OX, one-dimensional situation, under a force that's projection on OX is Fx equals F0 as, represented in the figure below, as function of x. At the origin of OX axis is placed a perfectly reflecting wall. A friction force of constant modulus Ff equals 1.00 newtons acts anywhere the particle is situated. The particle starts from the point x equals x0 is equal to 1.00 meter having the kinetic energy EC equals 10.0 joule. Question A. Find the length of the path of the particle before it comes to a final stop. Question B. Sketch the potential energy Ux of the particle in the force field Fx. Question C. Draw qualitatively the dependence of the particle speed as function of his coordinate x. Solution for problem 1. Question A. Find the length of the path of the particle before it comes to a final stop. It is possible to make a model of the situation in the problem, considering the OX axis vertically oriented having the wall in its lower part. The conservative force Fx could be the weight of the particle. One may present the motion of the particle as the vertical motion of a small elastic ball elastically colliding with the ground and moving with constant friction through the medium. The friction force is smaller than the weight. The potential energy of the particle can be represented in analogy to the gravitational potential energy of the ball, mgh. As is very well known, in the field of a conservative force, the variation of the potential energy depends only on the initial and final positions of the particle, being independent of the path between those positions. Since the ball is constantly subject to a force directed toward the wall and there is a friction force, the final location of the ball will be point x equal to 0, thus, all the kinetic energy of the particle plus potential will eventually go into the work of the friction force. That is, the relationship is true, Jf0x0 equals Ffd, where d equals Jf0x0 equals 20 meters. So, we have calculated the total distance based on the simple principle of energy conversion. Now let's calculate it based on ordinary kinematics. Apparently, we will have to calculate the sum of the terms of the geometric sequence. Option number 1. The initial velocity of the particle is directed upward. Then the total force acting on the particle will be F plus equals F0 plus Ff, that is, 10 plus 1 is equal to 11 newtons. Since the initial energy of the particle was J equals 10 joules, then the height to which the particle rises above the initial height x0 is equal to J divided by F plus or 10 divided by 11 meters, and the total maximum height h0 will be equal to 1 and 10 divided by 11 meters. Now the particle begins to move downwards. But now the force acting on the particle will be F minus equals F0 minus Ff, which is 9 newtons. Therefore, the kinetic energy of the particle before colliding with the wall will be E0 equals h0 times F minus equals 9 h0 joules. Now let's calculate the next height h1, to which the particle will rise. This will be E0 divided by F plus equals 9/11 h0, thus, we have calculated the coefficient of the geometric sequence, k equal to 9/11, and thus we can calculate the sum of the series of the geometric sequence starting from the first member. Of course, it must then be multiplied by 2, since the particle passes each height up and down. That is, we get the following sum. 2 multiplied by h1 and multiplied by the bracket 1 plus k to the first power, plus k to the second, and so on ad infinitum, which as a result is equal to 11h1. Now remember that h1 is equal to 9/11 h0. That is, the total result of the sum will be 9h0, but h0 was equal to 21 divided by 11 meters. Therefore, in meters we get 189 divided by 11 meters. It remains to add to this sum the initial h0 equal to 21 divided by 11 meters and the initial segment 10 divided by 11. We get that d is equal to 189 plus 21 plus 10 in the numerator and 11 in the denominator, which is exactly 20 meters. This gives us the result as in the case of a simple application of the energy conversion formula. It remains to consider the case when the initial velocity of the particle is directed downwards. I think now you know how to do it yourself. Question B. Sketch the potential energy U as function of x of the particle in the force field Fx. The relation U from x equals Fx by x gives the linear dependence of the potential energy to the position. If the motion occurs without friction, the particle can reach a point A situated at the distance delta apart from the origin in which the kinetic energy vanishes. In the point A the energy of the particles is entirely potential. The numerical value of the position of point A, furthest away from the origin, is delta equals 2 meters if the motion occurs without friction. The representation of the dependence of the potential energy on the position in the domain 0 to delta is represented in the figure. Figure during the real motion of the particle, with friction, the extreme positions reached by the particle are smaller than delta, because of the leak of energy due to friction. The graph in the figure is the answer to the question B. Question C. Draw qualitatively the dependence of the particle speed as function of his coordinate x. Solution. During the motion of the particle its energy decrease because of the dissipation work of the friction force. The speed of the particle has a local maximum near the wall. Denoting Vk the speed of the particle just before its kth collision with the wall and Vk plus 1 the speed just before its next collision, Vk greater than Vk plus 1. Among two successive collisions, the particle reaches its xk positions in which its speed vanishes and the energy of the particle is purely potential. These positions are closer and closer to the wall because a part of the energy of the particle is dissipated through friction. Xk plus 1 less than xk. Case 1. If the particle starts from the x0 position moving in the positive direction of the coordinate axis OX, its speed diminishes and its kinetic energy also diminishes while its potential energy increases to a maximum in the x1 position where the speed vanishes. During this motion the energy is dissipated due to the friction. The total energy Wx, for the positions x between x0 and x1 verify the relation Wx0 minus Wx equal Ff multiplied by x minus x0, the position x lying in the domain between x0 and x1. When the particle moves from x0 in the positive direction of the axis, the relation becomes next expression. So we have. Using provided data we have. The graph in the figure presents the dependence of the square speed on the position for the motion in the domain x between x0 and x1. The particle moves in the positive direction of the coordinate axis OX. This motion occurs until the position x1, when the speed vanishes, is reached. From the previous relation, in which we take the modulus of the speed 0, results x1 equal this expression. The numerical value for x1 is 21 over 11 meters. After furthest away position x1 is reached, the particle moves again towards the origin, without initial speed, in a speeded up motion having an acceleration of magnitude a minus equals fx plus ff over mass. After the collision with the wall, the particle has a velocity v1 equal in magnitude but opposite direction with the one it had before the collision. When the particle is at a point lying in the domain between 0 and x1 running from x0 to the origin, its total energy Wx has next expression. Because of friction, the value of the energy decreases from the one it had at x1 to the corresponding to the x position, we have The square of the speed has the expression. And the speed is. For the given data, in the domain, 0 to x1 speed square equal. Respectively speed is. The speed of the particle hitting a second time the wall according to previous. Is. And has the value. Concluding, after the first collision and first recoil, the particle moves away from the wall, reaches again a position where the speed vanishes and then comes back to the wall. The speed of the particle hitting again the wall is smaller than before, as in the figure. Denoting Vk the speed at the beginning of the kth run and xk the coordinate of the furthest away point during the kth run, the energy of the particle leaving the wall is. In the position xk after the k departure from the wall, the energy is. The variation of the total energy has the expression. So that. After the particle reaches the position xk the direction of the speed changes and, when the particle hits the wall. The energy conservation law for the xk position and the point in which the particle hits the wall gives. So that. Considering previous, this relation becomes. Between two successive collisions the speed diminishes in a geometrical progression with the ratio q. Using the data provided we have q equal. From k plus 1th collision the previous relation is written as. Considering these two, the ratio of the extreme positions in two successive runs is. For the kth run towards the origin, one may write the dependence of the square speed as function of the position as. Or, using the data we have. The evolution of the square of the speed as function on position is presented in the figure 1.10. And the evolution of the speed as function of the position is presented in the figure 1.11. The sum of the geometrical progression gives after the doubling and then subtracting of the x0 the total distance covered by the particle is. It results. The total distance covered by the particle is. Which allows us to find again the previous result. This was the solution to question C in the case of the initial direction of the particle's velocity from the wall. Similar reasoning can be applied during the initial movement towards the wall. This concludes our discussion of task number 1. 14th International Physics Olympiad Year 1983. IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. My Skype name is Eduard F. 1996. Problem 2. Different kind of oscillation, 8 points. Let's consider the electric circuit in the figure, for which L1 equal 10 mH, L2 equal 20 mH, C1 equal 10 picofarad, C2 equal 5 picofarad and resistor R equal 100 kilo. The switch K being closed the circuit is coupled with a source of alternating current. The current furnished by the source has constant intensity while the frequency of the current may be varied. Question A. Find the ratio of frequency Fm for which the active power in circuit has the maximum value Pm and the frequency difference delta F equal F plus minus F minus of the frequencies F plus and F minus for which the active power in the circuit is half of the maximum power Pm. The switch K is now open. In the moment t0 immediately after the switch is open the intensities of the currents in the coils L1 is I1 equals 0.1 ampere and L2 is I2 equals 0.2 ampere, the currents flow as in the figure. At the same moment, the potential difference on the capacitor with capacity C1 is U0 equal 40 volts. Question B. Calculate the frequency of electromagnetic oscillation in L1. C1. C2. L2 circuit. Question C. Determine the intensity of the electric current in the AB conductor. Question D. Calculate the amplitude of the oscillation of the intensity of electric current in the coil L1. Neglect the mutual induction of the coils, and the electric resistance of the conductors. Neglect the fast transition phenomena occurring when the switch is closed or opened. Solution for question A. As is very well known in the study of AC circuits using the formalism of complex numbers, a complex inductive reactance XL equal L omega J, where J equals square root from -1, is attached to the inductance L, part of a circuit supplied with an alternative current having the pulsation omega. Similar, a complex capacitive reactance XC equal -J over C omega is attached to the capacity C. A parallel circuit will be characterized by his complex admittance Y. The admittance of the AC circuit represented in the figure is next expression. Or in regular complex view it will be. The circuit behave as if has a parallel equivalent capacity C equals C1 plus C2 and a parallel equivalent inductance L equal L1 multiplied by L2 and divided by L1 plus L2. The complex admittance of the circuit may be written as and the complex impedance of the circuit will be expression 2.4. And the complex impedance of the circuit will be in formula 2.5. The impedance Z of the circuit, the inverse of the admittance of the circuit Y, is the modulus of the complex impedance Z. We can write in form of 2.6. The constant current source supplying the circuit furnish a current having a momentary value IT equal I multiplied by square root from 2 and multiplied by sinus omega t, where I is the effective intensity, constant, of the current and omega is the current pulsation, that can vary. The potential difference at the jacks of the circuit has the momentary value UT equal U multiplied by square root from 2 and multiplied by sinus omega t plus phi. Where U is the effective value of the tension and phi is the phase difference between tension and current. The effective values of the current and tension obey the relation 2.9. The active power in the circuit is P equal U square over R or Z square I square over. Because as in the announce, I is constant and U is constant, the maximal active power is realized for the maximum value of the impedance that is the minimal value of the admittance. The admittance is formula 2.12 has, as function of the pulsation omega, and the smallest value Y minimum equal 1 over R. For the pulsation we have omega m equal 1 over square root from L C. In this case we have C omega minus 1 over L omega equals 0. So, the minimal active power in the circuit has the value AR multiplied by I square and occurs in the situation of alternative current furnished by the source at the frequency FM equal 1 over 2 pi multiplied by omega m, which is 1 over 2 pi multiplied by square root from LC. To ensure that the active power is half of the maximum power, it is necessary that we have next conditions in form of 2.18. That is, the pulsation of the current ensuring an active power at half of the maximum power must satisfy one of the equations. The 2 second-degree equation may furnish the 4 solutions. Because the pulsation is every time positive, and because we have the only 2 valid solutions are, it exists 2 frequencies F plus minus equal 1 over 2 pi multiplied by omega plus minus, allowing to obtain in the circuit an active power representing half of the maximum power. The difference of these frequencies is delta F equal 1 over 2 pi multiplied by 1 over CL. The bandwidth of the circuit is the frequency interval around the resonance frequency having at the ends a signal representing 1 over square 2 from the resonance signal. At the ends of the bandwidth the active power reduces at the half of his value at the resonance. The asked ratio is in expressions 2.26. Because we have it results that omega m equal 10 power 5 radians per second. and Fm over delta F equal 150. These two last expressions are answers at the question A. The switch K is now open. In the moment t0, immediately after the switch is open, the intensities of the currents in the coils L1 is I1 equals 0.1 ampere and I2 equals 0.2 ampere in L2. The currents flow as in the figure. At the same moment, the potential difference on the capacitor with capacity C1 is 40 volts. Question B. Calculate the frequency of electromagnetic oscillation in L1, C1, C2, L2 circuit. The fact that immediately after the source is detached it is a current in the coils, allow us to admit that current's dependence on time will continue to flow through the coils. The capacitors will be charged with charges variable in time. The variation of the charges of the capacitors will result in currents flowing through the conductors linking the capacitors in the circuit. The momentary tension on the jacks of the coils and capacitors, identical for all elements in circuit, is also dependent on time. Let's admit that the electrical potential of the points C and D is U, T, and the potential of the points A and B is 0. If through the inductance L1 passes the variable current having the momentary value I1, T, the relation between the current and potentials is U, T, minus L1 multiplied by delta I1 over delta T equals 0. Formula 2.28, the current passing through the second inductance I2, T, has the expression U, T, minus L2 multiplied by delta I2 over delta T equals 0. Formula 2.29. If on the positive plate of the capacitor having the capacity C1 is stocked the charge Q1 T, then at the jacks of the capacitor the electrical tension is U, T and Q1 equals C1 U, formula 2.30. Deriving this relation it results, delta Q1 over delta T equals C1 delta U over delta T, formula 2.31. But delta Q1 over delta T equal negative I3. Formula 2.32, because the electrical current appears because of the diminishing of the electrical charge on capacitor, plate. Consequently IV equal negative C1 delta U over delta T, formula 2.33, analogous, for the other capacitor we have, I4 equal negative C2 delta U over delta T, formula 2.34, considering all obtained results we have, delta I1 over delta T equal U over L1, and delta I2 over delta T equal U over L2. Formula 2.35, and respectively we have delta I3 over delta T equal negative C1 second derivative U over delta T and delta I4 over delta T equal negative C2 second derivative U over delta T. Formula 2.36, denoting I5 T, the momentary intensity of the current flowing from point B to the point A, then the same momentary intensity has the current through the points C and D. For the point A the Kirchhoff rule of the currents gives I1 plus I5 equal I3. Expression 2.37, for point B point the same rule produces, I4 plus I5 equal I2. Expression 2.38, considering 2.37 and 2.38 results, I1 minus I3 equal I4 minus I2. Expression 2.39, and deriving this expression we can get expression 2.40. That is, we have ordinary linear equation of the second order to U. Expression 2.41. Using the symbols defined above we can simplify it in form of expression 2.42. Because the tension obeys the relation above, it must have a harmonic dependence on time as expression 2.43. The angular frequency of the tension is regular omega equal 1 over square root from L. See expression 2.44. Taking into account the relations 2.43 and 2.36 it results that for I3 and I4 we have expressions 2.45. And for derivatives from I1 and I2 there are expressions 2.46, what leads to the result antiderivatives in form of expressions 2.47. In the expression above, A, M, N and delta are constants that must be determined using initially conditions. It is remarkable that the currents through capacitors are sinusoidal but the currents through the coils are the sum of sinusoidal and constant currents. In the first moment the initials are as in expressions 2.48, because the values of the inductances and capacities are as in expressions 2.49, the equivalent inductance and capacity are as in 2.50 and 2.51 respectively. From 2.44 omega equal 10 power 5 radians per second. The value of the angular velocity allows calculating the value of the requested frequency, which is omega over 2 pi. That was solution for question B. Question C. Determine the intensity of the electric current in the A-B conductor. Solution for question C. If the momentary tension on circuit is like in 2.43, one may write expressions 2.54, from the currents 2.47 is possible to write that currents I01 and I02 are as in 2.55, on the other side is possible to express 2.39 in form of 2.56. An identity as 2.57 is valuable for any value of the argument alpha only if we have 2.58. Considering 2.58, from 2.56 it results 2.59, for the last equation it results that the circuit oscillate with the angular frequency in the relation 2.44. Adding relations 2.55 and considering 2.54 and 2.59 results expressions 2.60. The numerical value of the amplitude of the electrical tension results by summing the last relations from 2.54 and 2.60. Which is giving us expressions 2.61. The numerical value of the electrical tension on the jacks of the circuit is 2.62, and consequently from 2.54 results 2.63, 2.64 and 2.65. From 2.55 we have 2.66. The corresponding numerical values are in 2.67. The relations 2.47 becomes 2.68. The currents through the coils are the superposition of sinusoidal currents having different amplitudes, and a direct current passing only through the coils. This direct current has the constant value 2.69 as in the figure 2.2, the alternative currents through the coils has the expressions 2.70, the currents through the capacitors has the forms 2.71, the current I5 has the expression 2.72. The value of the intensity of I5 current is the answer from the question C. The initial value of this current is 2.73. Question D. Calculate the amplitude of the oscillation of the intensity of electric current in the coil L1. Neglect the mutual induction of the coils, and the electric resistance of the conductors. Neglect the fast transition phenomena occurring when the switch is closed or opened. Solution for question D. The amplitude of the current through the inductance L1 is 2.74, which represents the answer at the question D. Now we finished all questions for problem 2. 14th International Physics Olympiad Year 1983 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. My Skype name is Eduard F. 1996. Problem 3. Prisms, 7 points. Two dispersive prisms having apex angles a 1 equals 60 degrees and a 2 equal 30 degrees are glued as in the figure below. Angle C equal 90 degrees. The dependences of refraction indexes of the prisms on the wavelength are given by the relations n1 and n2, where a 1 equal 1.1, b1 equal 10 power 5 square nanometers. A 2 equal 1.3, and b2 equal 5 by 10 power 4 square nanometers. Question A. Determine the wavelength lambda 0 of the incident radiation that passed through the prisms without refraction on a C face at any incident angle. Determine the corresponding refraction indexes of the prisms. Question B. Draw the ray path in the system of prisms for 3 different radiations lambda red, lambda 0, lambda violet, incident on the system at the same angle. Question C. Determine the minimum deviation angle in the system for a ray having the wavelength lambda 0. Question D. calculate the wavelength of the ray that penetrates and exits the system along directions parallel to DC. Question A. Determine the wavelength λ0 of the incident radiation that passed through the prisms without refraction on AC face at any incident angle. Determine the corresponding refraction indexes of the prisms. Solution. The ray with the wavelength λ0 passed through the prism system without refraction on AC face at any angle of incidence if n1 of λ0 equal n2 of λ0. Relation 3.1. From here we have relation 3.2. The wavelength λ0 has correspondingly the form 3.3. Substituting the furnished numerical values λ0 is 500 nanometers. The corresponding common value of indexes of refraction of prisms for the radiation with the wavelength λ0 is 1.5. The relations 3.4 and 3.5 represent the answers of question A. Question B. Draw the ray path in the system of prisms for three different radiations λ red, λ0, λ violet, incident on the system at the same angle. Solution. For the rays with different wavelength having the same incidence angle on first prism, the paths are illustrated in the figure 1.1, since for the wavelength λ0 equal to 500 nanometers both refractive indices are equal to 1.5, the angle of refraction on the first face AD will be less than the angle of incidence according to the Snell's formula. Then the second face array will pass without deflection, as shown in the figure. Next, since n1 λ red is less than n1 λ0, on the first face AD the red ray will go above the zero ray. And further, since n1 λ red is less than n2 λ red, the red ray will deviate upward after refraction at the boundary AC. And it will deviate even more at the boundary with air. The violet ray behaves the opposite way. Since now n1 λ violet is greater than n1 λ0, on the first face AD the violet ray will go below the zero ray. And further, since n1 λ violet is greater than n2 λ violet, the violet ray will be deflected downwards after refraction at the AC boundary. And it will be deflected even more at the BC boundary with air. So the draw illustrated in the figure 1.1 represents the answer of question B. Question C. Determine the minimum angle of deflection in the system for a beam with a wavelength of λ0. Solution. Let's complete our prisms to a triangular one with an upper angle A' equal to 30 degrees. For a wavelength of λ0, we have n1 λ0 equals n2 λ0 equals n equals 1.5. Let's mark the angles I1, I2, J1 and J2 in the figure. Then, from Snell's law of refraction of rays, we have the following two relationships. In general, the angles I and the angles J are not equal to each other. But in this case, when the angle I1 changes in one direction, the total angle of deflection will decrease, and in the other direction, it will increase. That is, at different angles I, the minimum is not observed. It can only occur if I1 is equal to I2, and J1 is equal to J2. But in this case, J1 is equal to J2 is equal to the angle A' in half. From the figure it is clear that the total angle of deviation will be equal to I1 plus I2 minus A', which as a result of all the numerical substitutions gives the angle of deviation equal to 15.7 degrees. This is the solution to the question of C. Question D. Calculate the wavelength of the ray that penetrates and exits the system along directions parallel to DC. Solution. Using the figure, the refraction law on the AD face is 3.11, the refraction law on the AC face is 3.12, as it can be seen in the figure, and I1 equal 30 degrees. Also R1 plus R1' equal a 1. Substituting 3.13 and 3.15 in 3.12 it results 3.16, or 3.17, because of 3.11 and 3.15 it results that 3.18 and 3.19, putting together the last three relations it results 3.20. Because angle A1 is 60 degrees and angle 2 is 30 degrees, relation 3.21 can be written as this expression. Or as expression 3.22, considering the relation's numeric values for n1 and n2 and operating all calculus, it results quadratic equation 3.23 to lambda square. Solving it, one determine the wavelength lambda of the ray that enter the prism system, having the direction parallel with DC, and emerges the prism system having the direction again parallel with DC. That is lambda equal about 1.2 micrometers. This represents the answer of question D.